Welcome back to NBC Weather Plus You. I'm meteorologist Elise Finch. Believe it or not, altitude has a lot to do with how your favorite breakfast, lunch, or dinner is made. Mike McKee from the University of Central Florida gets down to the nitty-gritty.
You know, if you've ever tried to cook and you've gotten some of these baking recipes, you might have noticed that there's like a high altitude recipe. Now why would that be the case? Well, really this has to do with the atmosphere, and our atmosphere really goes way up, 700 miles up into the sky. All right, now what makes up our atmosphere? A lot of molecules: oxygen, nitrogen, argon, a little bit of carbon dioxide, a little bit of water vapor, but all these we can represent with some molecules here, or balls that represent the molecules, and these things go flying around. Now, thing is, we've got gravity, and the gravity pulls each one of these things down to the ground. Even though they've got a lot of energy to fly up, just like I can toss the ball up into the air, our gravity pulls down on each one of these molecules, keeping the atmosphere in place. All right, now, depending on the different size here, some of them can go a little farther, some of them a little less, but they all are held in place by Earth's gravity. Now, if you go to the moon, there's no atmosphere, not because there's no gravity. A lot of people think that because there's no atmosphere, there's no gravity. No. It's actually because the gravity is so weak that it has a very difficult time holding on to these molecules, and they can escape away from the atmosphere of the moon, leaving nothing. On Earth, it requires about 25,000 miles per hour. The speed, 25,000 miles per hour, for it to leave the atmosphere. So most molecules can't get to that speed for that to happen. Now, if you're cooking, in order to get something to cook, you're oftentimes boiling water. And our atmosphere has an effect on that. Now, I've got a pot of water here, and we're going to do a simulation with this to see what happens when we take our water and we go from the surface of the Earth down here at sea level, where the pressure is about 1,013 millibars, and we're going to take it far up into the atmosphere. Now, we could drive in a car and go up into the mountains, but we're going to simulate this with a vacuum pump. We've got here some boiling water. Now, here's the deal. The atmosphere is pushing down on this water, okay, 14.7 pounds per square inch. If we've got a quarter, I'll put that on my hand here, that represents about the size of a square inch. So there's a column of air that goes all the way to the top of the atmosphere, way up there, 700 miles up, that in total weighs 14.7 pounds. All right, now if we made like a little here of quarters all the way across the top, we would have, I don't know, maybe 100 pounds or so of pressure pushing down on the top of our water. Now, that's going to keep the water from boiling here at sea level until the pressure of the water gets up to about 212 degrees. That will then cause the vapor to sort of explode out in those little bubbles, and that overcomes the force of the pressure of the atmosphere. So, if I take this and reduce the pressure, then we're going to see the water boil at a lower temperature. All right, so we're going to do this. I've got here a beaker, and obviously this beaker is not going to fit into this bell jar. So we're going to pour a little bit of this water in to the beaker. So I'm going to put this here so you guys can see this, and pour a little bit in. Now you notice it's hot, but it's certainly not boiling here at sea level. I'm going to put this inside of the bell jar, and then I'm going to cap this. I'm going to also place in a probe here, and the probe is going to measure the temperature. All right, so put that in, and then I'll cap this, and I'm going to start to reduce the pressure inside. Now this is going to simulate going up into the atmosphere. All right, so we're now climbing into the atmosphere, and let's see what happens. And we see, holy moly, it's actually starting to boil. As the pressure comes off of that water, it allows the water to start to vaporize and boil. Okay, now here's the effect of this. If we're farther up in the atmosphere, that means obviously the temperature is not 212 degrees. It's at a temperature below 212. So if you're cooking, you got a couple effects here. You've got one effect of the water is vaporizing out at a lower temperature. And so that's actually drying the food out. And if you've ever put like a piece of bread inside of a microwave oven, you know that it gets really hard and nasty and everything. Well, that's not so good for baking a cake. So you have to add more water because this vaporization goes on at a lower temperature. You also have a second effect here of the fact that it's not getting to as high of a temperature, and that's causing the food to take longer to bake. So, if you take a look at the back of this cake box, you see that you have to bake it for a longer period of time, and you also have to add more water to the recipe to make it work. So see, the atmosphere does have an effect on even things like baking. It's not just altitude that makes a difference in the boiling point of water. Even differences from high pressure to low pressure, if you've got a storm that moves across you versus nice sunny days, that can also affect the boiling point of water. In fact, between a low pressure and a high pressure system, you can have about a 3-degree difference in the boiling point of water. I'm Mike McKee for Weather Plus U.